Okay, and so now we can welcome our next speaker, Hari Subramoni from Ohio State University, with their session about accelerating MPI all-reduce communication with efficient GPU-based compression schemes on modern GPU clusters. I'd like to point out that Hari is an assistant professor in the Department of Computer Science and Engineering and has published well over 120 papers in international journals and conferences. Take it away.
Sure. Hey, Phil, thank you for the kind introduction. Sorry, folks, that I'm not able to see you in person. Hopefully, in future years, we'll kind of go back to the in-person mode. Again, feel free to ask any questions, comments, or thoughts that you may have during the presentation. I'm more than happy to take them. I'm sure all of us are more than capable of talking for hours on end if led to our own devices. So again, thank you, Yanfei, for the nice segue. And it's good to see that some of the work that we've been doing here regarding compression is kind of making its way upstream into MPitch as well. So in this talk, we'll be presenting our work on how we accelerated all-reduce communication with GPU-based compression schemes. So any questions that, have you ever thought why compression, folks? Have you ever thought, hey, why do you need compression on the fly? Okay.
I saw just too much data, right?
Too much data, yes. So if you can take a look at the trends in modern HPC systems, you have a lot of compute power, right? Significant amount of compute power. But if you look at the amount of communication bandwidth going from one compute node to the other, that is not scaling as much. Recently, if you guys noticed at GTC, the intra-node, let's say, or intra-rack performance is like pretty good with the availability of NVLink, NVLink 2, NVLink 3, like various generations of it. But if you look at the scale-out performance, if you want to go to maybe hundreds or thousands of nodes to train these large language models or for any HPC work, you will end up hitting your InfiniBand or any other high-speed Ethernet or OmniPath, OPX bottleneck. So if you look at it, your compute performance is increasing much, much, much faster than communication is able to keep up. This, at a high level, is creating islands of computation. So this kind of a notion prevents scaling out. Like a few dozen nodes may be perfectly fine, but if you want to go to hundreds or thousands of nodes, the scale out becomes a problem and your network bandwidth becomes a challenge. So in most cases, we might be using blocking communication. So when this communication actually happens, your compute devices are actually, let's say, twiddling their thumbs, so to speak. They're not effectively doing anything useful. So broadly, what we are trying to see here is, instead of making these devices twiddle their thumbs, can we make them do something productive? And let's say, compress the data unbeknown to the application inside the communication runtime, send the compressed data over the network, decompress it or uncompress it on the receiver side, and give back the data to the higher level application without the application ever having known that all of this fancy stuff happened in the communication runtime. And all of this while ensuring that your application converges or the loss does not go higher. So this is the overall premise of the work that we are trying to do. So far in the MPitch communication runtime, we have support for on-the-fly compression for basic point-to-point communication operations, various collective operations like all-to-all, all-gather, scatter, broadcast, and so far we were focusing on, let's say, pure communication only collective or point-to-point operations. Right now, we have kind of stepped into trying to look at communication plus computation collective operations like reduction. Okay. So we propose like two different design approaches. So one is the ring all-reduce with collective level compression. The other is the recursive doubling all-reduce. So we took two different popular reduction algorithms and tried to apply compression to that. So as all of us know, reduction is fairly popular both in HPC as well as deep learning applications. If you look at existing algorithms for AllReduce for transferring large amounts of data, so let's say if you look at distributed data parallel deep learning or the image stacking application that Jan Fei talked about, all of them do suffer from poor performance because of a limited network bandwidth. Okay, so obviously what you can do is, hey, I already have point-to-point compression support. Can't I just leverage that and layer my collectives on top of that? Since, as you saw in the previous slide, collectives are layered on top of point-to-point, and we already have point-to-point compression support, so why not just reuse that? So the problem with relying on point-to-point level compression is that there is a lot of semantic mismatches, and there is a lot of optimization potential that you lose out on if you just build your collective compression on top of your basic point-to-point based algorithms. And this we have seen with various other compression schemes that we developed for other collectives like all-to-all, all-gather, reduce, scatter, broadcast, so on and so forth. So here, what we want to do is we want to integrate collective compression support at the collective level so that you are able to save on multiple compression operations that you have to do back to back if you do compression at the point-to-point level. So with that, let's look at some of the design approaches that we took for the ring-based AllReduce at the collective level. So if you look at it, what are the high-level trade-offs here, the pros and cons? So compression can obviously reduce the data size, which can lower the pressure on the network, which has limited bandwidth. So if you look at the existing point-to-point based implementation, it has a limitation of overlapping compression and decompression kernels across multiple send-receive operations. And there is also a small hindrance in effectively using non-blocking send and receive operations in AllReduce. So we want to take the compression, which is at the point-to-point level, to the higher level collective level inside like various AllReduce algorithms. And once we did that, we actually looked at the compression library. So we are using the ZFP compression library from Lawrence Livermore National Labs, which is a lossy compression library. So we optimize the CFP compression library to enable execution of compression and decompression and reduction kernels on multiple CUDA streams. So when you look at various compression algorithms, people who wrote that may have been really good with designing a compression algorithm, but they may not have had the necessary system expertise to figure out that, hey, if I launch all of this on one GPU or one CUDA stream, it is going to get serialized. So we address that bottleneck, and we use multiple CUDA streams to enable faster execution of compression, decompression, and reduction kernels. So this usage of multiple streams at a system level allows us to achieve overlap between these various kernels as well as send-receive operations. So that is the algorithm at a higher level. So let's take a look at the data flow for the ring AllReduce with the collective level compression. So initially, each GPU would have some data. We split that into multiple chunks. And in the first phase, we aggregate the values on each GPU using like a ring algorithm. So once the aggregated values have been transferred to various GPUs, as you see here, we will perform compression on these different chunks. And the compressed and aggregated value would be transferred across the various GPUs on one node, and then finally on multiple nodes, so that your reduced data will keep on adding up as you see in this figure. Finally, at the end of all the different steps, each GPU is going to have the reduced value which it collected from all the other GPUs, as you see in this particular step. So this is an example of how we implemented the basic ring-based AllReduce with the collective level online compression. So this is mostly applicable in the medium to very large message range. We then looked at another algorithm, the recursive doubling algorithm, which typically is used in the smaller message range with collective level online compression. And this shows the data flow for that particular algorithm. So in this algorithm, what we would do is we like specific pairs of processes would exchange the messages with each other in a pairwise manner. As you see here, let's say 0 will talk to 1, 1 will talk to 0. The whole data on each GPU is compressed and decompressed. So fewer data exchanges are needed across all the processes, thus fewer compression operations. So by using such a method, we are able to achieve better overlap between the compression, decompression, and the reduction kernels, as well as the send receive operations. So finally, at the end of the various steps, let's step 1, step 2, step 3, and step 4, we are able to have all the data available on all GPUs with good overlap of computation and communication. Okay. So at a high level, these are the two algorithms that we created. Now, let's look at the performance evaluation. So we did two levels of evaluation at the benchmark level and at the application level. And all of this was done in the context of the MVAPITCH Plus MPI library, which is being used by a lot of organizations. I'm sure all of you are familiar with that. We used multiple systems for doing our evaluations. So most of the work was using NVIDIA's GPUs. So we used V100 GPUs on the Pitzer system at Ohio Supercomputing Center, A100 GPUs on a local system called MRI at The Ohio State University. We used the RTX GPUs on Frontera, as well as the V100 GPUs on the Larson system at Lawrence Livermore National Labs. We were using the MVAPITCH MPI library. So we used AllReduce in OSU microbenchmarks for the benchmark level evaluations. The application level evaluations were using distributed data parallel training of DNN models with PyTorch. So in this slide, we look at the kind of performance benefits that you get at the microbenchmark level using the ring, as well as the recursive doubling AllReduce with collective level compression. So these were taken on the Pitzer supercomputing system with 4, 8, and 16 GPUs. So that is 2, 4, and 8 nodes with 2 processes per node. So at the very largest scale, what we see, again, broadly, if you see across the various message sizes, the compression enabled algorithm. So if you look at the red line, RD, and the orange and the yellow lines, you will see that they are much better in performance compared to the red line, which is obviously going to be the case because we are using lossy compression, which means that we'll be able to cut the data significantly. So if you compare the red, orange, and yellow, you see that as the compression rate increases from 16 to 8, the communication time reduces for the recursive doubling algorithm, and the same trend is observed with the ring algorithm as well. So as the compression rate increases, there's the gray is no compression, the blue and the green are with different rates of compression. So we can see that the time taken for completing the operation reduces significantly. And we also observe that different algorithms do better for different message sizes and system sizes. So we need to have careful selection of the algorithms depending on the system size and the message size. So this is based on our paper, which has been accepted to be presented at the International Supercomputing Conference later in May in Germany. So this is the same performance that we see on the MRI system. So this is with 100 GPUs. So broadly, you can see that the trends are still similar. The algorithms with compression are able to outperform the baseline version, which is blue. So if you look at the ring algorithm, it does perform the best for the very large message sizes. If you look at recursive doubling, that performs better for the smaller message sizes here. So we have implemented compression for both of these algorithms, and we choose the appropriate algorithm based on the system size as well as the message size. So this is the evaluation on the RTX GPUs. So broadly, the trends remain the same. If you look at the ring AllReduce with compression, it's able to reduce the latency by up to 69 to 70%. If you look at the recursive doubling algorithm with compression, it is able to reduce the latency by up to 75% on various GPUs. So here we were able to go to larger scales because of the availability of more number of nodes. So this is on 16 nodes and 4 processes per node, because each node had about 4 GPUs on this particular system. So finally, this is the evaluation on the Larsen supercomputing system. So again, the trends are very similar. Overall, we are able to get good performance. And here on Larsen, we were able to scale out even further. So we were able to try the experiment on 64, 128, and 256 GPUs, which is up to 64 nodes with 4 processes per node. So we saw somewhere between 70 to 75, 76% reduction in overall latency compared to the original baseline algorithm. So far we were looking at our initial evaluations where we were comparing the baseline collective algorithm without any compression with collective level compression that we had designed. So now we are trying to compare the performance of point-to-point compression and the compression at the collective level. So one thing to note here is that with point-to-point compression, each message will have to be compressed and decompressed because of the layering of MPI, because the point-to-point level does not have any state information as to what happened before and what is going to happen next. So each message will have to be compressed and decompressed. So there is a lot of additional steps involved and a lot of additional computation involved for compression and decompression at each step. So if you look at the collective level compression, which is the blue and the green lines, compared to the point-to-point level compression, which is the orange and the yellow lines, across various systems and for various message sizes, various number of GPUs and various algorithms, it is very clear that the collective level compression offers significant benefits over the point-to-point based compression. So those are the evaluations at the micro benchmark level, but that may not tell you much because we are using lossy compression. It is like more or less expected that if you cut the data, your overall communication time does reduce. A better evaluation will be to look at the actual application level to see if an application is able to tolerate this level of loss. So we have some slides showing the accuracy loss or lack of it a little later. So first, let's look at the basic performance. So here we are looking at the distributed data parallel training performance on Pitzer with V100 GPUs using the CFAR10 dataset for a batch size of 128 and a learning rate of 0.001. We use the MPI backend with the proposed ring and recursive doubling based AllReduce with online compression, and we compare that against the baseline approach. So the blue line is the baseline approach. This is for like different number of GPUs for different models. So this is the wide ResNet model. This is the ResNext model. This is the ConNext model. So if you look at the performance of the baseline approach compared to the various compression schemes and algorithms. So here we look at recursive doubling with different compression rates and ring with different compression rates. So broadly, you see that depending on your system size and the number of GPUs, either the recursive doubling algorithm or the ring algorithm does best. So overall, we were able to save somewhere between 25 to 35% in overall execution time for distributed data parallel deep learning training. Okay, so all of this is great, but the question is, how does your accuracy, is your accuracy affected significantly? So this is an important point, especially when you are using lossy compression. If you are using lossless compression, it is much less of a concern because it is not expected to degrade the accuracy of your final trained model significantly. But if you are using a lossy compression, then this is something that we need to pay careful attention to. So here we look at the accuracy of your baseline model, which is the blue one, with your various other compression enabled solutions for different algorithms. So one thing that is very clear is that if you compress too much, so for the lower the number here, the higher the compression. So if you compress your data too much, which means that there is going to be a lot of loss, you see that the accuracy significantly degrades from your baseline performance, which is somewhere around here. So for all the three models, you see that using a very high rate of compression results in a reduction in accuracy. Of course, if you use that rate of compression, the benefit is that your overall training time goes down, but it does not help because your accuracy of the model significantly degrades. So what we have to do is we have to figure out what is the best accuracy for the model for the particular system size, message size, and the scale of the training that we are doing. So broadly, what we saw was that a compression rate of 16 or 8 does pretty well. But once you go beyond that, let's say if you force a compression rate of 6 for the recursive doubling algorithm with CFP, the accuracy significantly degrades as the number of epochs increases. So if you're able to hit that sweet spot, where you are able to compress the data enough and reduce the overall compression time, as is shown here. So for instance, if you look at the green line, which is ring with a rate of 16, so here you see that you see benefits in your training time compared to your default execution time here, while you are able to maintain a good training accuracy. So if you want to be a little bit more aggressive, you can use like a higher rate of maybe 8 or so. So here you see that sometimes you are still able to tolerate the rate 8. So especially if you look at the orange line with the recursive doubling algorithm and the ZFP. So the orange line kind of trends the blue line in terms of the accuracy. So the blue line is the baseline without any compression whatsoever. So the MPI library provides you environment variables to tweak and tune these different parameters. So you're able to significantly reduce your overall data parallel distributed deep learning time, as you can see here, while you are able to maintain the accuracy of your trained model as you increase the number of epochs. So at a high level, this is the work that we have done so far. So let me summarize what we've been able to do. So we took the concept of compression, and we applied that to an MPI communication runtime. The major benefit here is that this compression is done on the fly and there are no application changes that are needed. So once you have written an application, you don't have to use a newer interface. You can this would still be you can change the MPI libraries. Things would still work fine. And what we used was we ensured that we were using the GPU cycles when the GPU was idle to good use, and we were able to compress the messages on the fly once you received it from the application, send it over the wire, decompress it, and give it back to the application at the receiver side. All this while ensuring that the accuracy or the effectiveness of the trained model still remains to the baseline version. Through this, we were able to show anywhere between 60 to 80% reduction in execution time at the microbenchmark level. And for PyTorch distributed data parallel deep learning training for different algorithms, we were able to show about 30 to 35% improvement in the or reduction in overall training time. So far we have added support for various different forms of on-the-fly compression, point-to-point level compression, collective level compression for all-gather, all-to-all, reduce scatter, broadcast, and now AllReduce. Most of this was done for the NVIDIA GPUs, but we are now working on the frontier system to kind of port all of these solutions over to the AMD GPUs as well. So one of the things that we are also exploring is trying to see if similar solutions are applicable to Intel-based system using their one API interface. So you will see these solutions coming out of our lab in the near future. So with this, I kind of come to the end of my talk. I think we have a few minutes for Q&A. I'll be more than happy to take any questions if you have it. Thank you for the patient listening.
Okay, I have a quick question. I mean, so any estimation about the compression ratio for the different rate? For example, for rate 8, what is the size comparison between before and after the compression?
I don't have the numbers off the top of my head exactly, but I think the data would get compressed around 33% or something like that for rate 8, if I remember correctly. I can check the paper and get back to you.
Okay, thanks.
Sure. So again, sorry, was there a question? So this is again lossy compression. We are working. So we had presented this at the GPU Technology Conference a few weeks ago. So there was a lot of interest from the community to see if we can include support for lossless compression schemes as well. So that is something that we are trying to create by having a compression abstraction layer inside MVAPage and trying to see if we can add support for different kind of compression libraries. For instance, can we use NVComp from NVIDIA? Can we use MPC? Can we use ZFP? And the other libraries that Yanfei mentioned. And can this be made applicable to different GPUs as well? So we would like to have a GPU as well as a compression abstraction layer in the communication runtime so that we are able to apply this on different kind of platforms and explore the benefits.
I have a question. Do you have a sense for how like this would compare to something like quantization, where the model itself uses like lower precision representation of vectors, where like effectively it's a similar problem where you're losing fidelity of the data, but you maintain accuracy, right?
Correct.
Rather than compressing. So is that, I'm wondering if you've looked into that and how this compares to that.
Yes, we have looked into it. So quantization happens at the model level. So this is model agnostic. So if you want to do quantization, you will have to apply the same technique to every single model. So this would be agnostic to that. The other thing that we are trying to see is once you have this quantized model, can this provide a complementary solution? So if you give a quantized model to and a communication runtime which is capable of compressing those kind of data, will we get further benefits? So that is another thing that we are exploring. Does that answer the question?
Yeah, it does. Thank you.
Thanks, Raghu. Any other questions, thoughts, or comments?
I see a hand up from Zhou.
Hi, Harry. Very good talk. Can you hear me?
Yes.
Yes.
Yeah, I really appreciate your talk. However, as Yan mentioned, we already have the paper covering how to integrate lossy compression into both the rate cursor doubling and the ring-based AllReduce operation. It is accepted by ICS and being available on archive since last August. And I'll attach the paper link here. So could you please comment on this?
So honestly, we were not aware of the work that you did. So we have been we first published the AllReduce work in IPC in 2020. It was a short paper. I can refer you to that link if you would like to. So honestly, I was not aware that you were doing this work. So just when Yanfei was mentioning that you had a paper at ICS, I asked my student to take a look at it. So I was not aware. It just looked like it just happened that both of us were exploring the same concepts at the same time, which is like a happy coincidence.
Yeah, I see. For your paper accepted by IBC, I see that it is not about AllReduce, right?
Sorry?
You mentioned that you have a paper accepted by IPC, right? And I just checked that it is not about AllReduce.
Sorry, it is what about it is?
it is not about AllReduce.
I thought it. Okay. Jejun, do you want to email me offline? I can talk with you. Okay.
Okay, sure,
Okay.
no
So
problem.
okay. We didn't copy your work. Let me be very
Oh,
blunt. If
I
that is your
understand,
question. Okay?
just a coincidence. Yeah,
Yes.
sure.
So let me be very blunt. We didn't copy your work. We have been working on compression for about 3 to 4 years right now at the point-to-point level and at various for various collectives. I think it just happened to be a happy coincidence that both of us were looking at the same kind of algorithms at the same time. I was not aware of the archive paper either, so we have been looking at this for quite some time. So trust us when we say that we didn't copy your work, okay? But
Yeah, sure.
good to know that you are also exploring similar concepts. All right.
Yeah, thanks for answers.
Sure.
Great. I did see a question, a hand raised for Benson.
You mentioned also looking at lossless compression.
Yes.
Yeah, how much more expensive that will be? And I guess you showed us some speed up. So the accuracy stuff will probably remain 100% with lossless, but how much more expensive is it in terms of speed up?
So with lossless compression, the amount of data that you can compress actually relies on what you're trying to communicate. So the data set makes a significant difference on the performance of lossless compression. In this particular use case, we did not see that much benefits with lossless compression. And one of the reasons we went with lossy, or another reason that we went with lossy compression was that the deep learning applications can tolerate some level of loss. From our previous evaluations with various other applications, we had a notion of where lossy versus lossless compression would show benefits versus disadvantage. So we thought it is better to go with lossy compression for this particular use case.
Thank you.
Yeah. Thank you, guys. Jiajun, if you don't mind, please do email me offline. I can show you the details of the work that we did and its antecedents. Okay?
Okay, sure, no problem.
Thank
Thanks.
you. Yeah. Thank you for your patient listening, guys. I think, Phil, I'm done. If there aren't any other questions, I think we can move on.
Perfect. Thank you.